You're standing in the electrical aisle of a building supply store, looking at a dizzying array of spools, cables, and conduits. They all look vaguely similar, but the choice you make here is one of the most critical safety decisions in the entire construction process. Faulty or inappropriate wiring materials are a leading cause of building fires worldwide. So, how do you navigate the options between copper and aluminum, between Romex and THHN, between PVC and steel conduit? In this video, we're going to demystify electrical wiring materials from an electrician's perspective. We'll explain not just what each material is, but the underlying electrical theory that dictates its use: conductivity, ampacity, and insulation resistance. By the end, you'll understand the National Electrical Code's rationale, be able to identify the right cable for the right application, and know the pro-level installation secrets that ensure a safe, reliable, and code-compliant electrical system for decades to come. Let's start with the heart of the matter, the conductor itself. This is the metal wire that actually carries the electrical current. The undisputed king of conductors is copper. Why? Because copper offers an exceptional balance of high conductivity, mechanical strength, and ductility. It's easy to work with, it makes reliable connections, and it's highly resistant to corrosion. You'll see it in two main forms: solid core and stranded. Solid core wire, a single solid piece of copper, is rigid and is typically used for permanent, behind-the-walls installations in residential branch circuits where it won't be moved. Stranded wire, made up of many thin copper threads bundled together, is flexible and is used for appliance cords, wiring inside fixtures, and in commercial applications where wires need to be pulled through many bends in a conduit. The alternative to copper is aluminum. Aluminum is lighter and less expensive, but it has lower conductivity and a higher coefficient of thermal expansion. This means it expands and contracts more with heat than copper does. This was the root cause of the aluminum wiring crisis in the 1960s and 70s. The connections would loosen over time as the aluminum expanded and contracted, leading to arcing, hot spots, and fires. Modern A800 series aluminum alloys and specialized antioxidant paste have made aluminum safer for specific applications like service entrance cables and large feeder circuits. But it requires special connectors rated for aluminum and an electrician who knows the precise torque specifications for the terminals. A pro tip from master electricians is to never, ever use a standard CO or outlet or switch with aluminum wire. You must use devices specifically marked as safe for aluminum. Now, the conductor is useless and incredibly dangerous without its protective layer, the insulation. The insulation's job is to contain the electrical flow within the conductor and protect it from moisture, heat, chemicals, and physical damage. The type of insulation dictates where and how a wire can be used. The most common insulation you'll see is THHN, which stands for thermoplastic, high heat resistant, nylon coated. This is the standard single conductor wire used inside conduit and cable trays in commercial and industrial buildings. Its cousin, THWN, is also rated for wet locations. For residential wiring, the most common cable is an MB, which stands for non-metallic sheath cable. You know it by the brand name Romex. This is a factory-assembled cable containing two or more insulated conductors, typically THHN wires plus a bare ground wire, all wrapped in a flexible plastic jacket. It's quick and cost-effective for dry, protected indoor locations like inside wall cavities. However, a common and dangerous drafting mistake is to specify an MB cable in a damp location like an unfinished basement or garage where it is subject to physical damage. This is a direct NEC violation. For these areas, you would step up to a more robust cable like MC or metal-clad cable. MC cable has insulated conductors bundled together, but with an outer spiral wound or corrugated metal armor that provides excellent physical protection. This brings us to the raceway systems, the protective pipes that hold the wires. The raceway is not just a sleeve, it's a critical part of the electrical system, providing physical protection, supporting the wires, and allowing for future circuit changes by pulling old wires out and new ones in. The most common type is EMT, or electrical metallic tubing. This is the thin-walled, rigid steel conduit you see in commercial buildings. It's strong, lightweight, and corrosion-resistant on the inside. For areas subject to severe physical damage or wear embedded in concrete, you use INC or RMC, which are thicker-walled, heavy-duty steel conduits. For corrosive environments, like chemical plants or direct burial in the ground, PVC conduit is the material of choice. It's non-metallic, so it won't rust, and it's glued together with solvent weld to form a watertight seal. A critical pro tip for any conduit installation is to never fill it more than 40% of its cross-sectional area when you have more than 2 wires. This is the NEC's fill capacity rule. Overfilling a conduit creates excessive heat buildup during operation and makes it impossible to pull the wires without damaging the insulation, a recipe for a future failure. Beyond the basic wires and pipes, we have the components that ensure safety at the endpoints. The device's outlets and switches must be matched to the wire and the application. A standard 15-amp duplex receptacle is not suitable for a kitchen countertop or a bathroom. You need a GFCI to protect against ground faults. An outlet for an electric dryer or range must be rated for the higher amperage and a specific plug configuration. The connections themselves are arguably the most critical point in the entire system. The NEC requires all connections to be made inside an approved junction box, and the box must remain accessible. The preferred method for a reliable, permanent connection is using a wire nut, but not just twisted on by hand. A pro tip is to use a torque-sensing electric screwdriver or a skilled hand to pre-twist the conductors before applying the wire nut, ensuring a gas-tight connection that won't loosen over time. For aluminum wires, as mentioned, you must use specially rated purple wire nuts or Lumicon connectors. A common and catastrophic on-site mistake is the backstab connection on the back of a receptacle, which is a notoriously weak and failure-prone point. The correct method is to use the screw terminals on the side of the device. To summarize the key takeaways: 1. Copper is the preferred conductor for its safety and reliability, while aluminum requires specialized knowledge and components. 2. Match the cable type to the environment: 10 MB for dry, protected areas, and MC or conduit for damp or exposed locations. 3. Conduit fill capacity is a critical safety rule that prevents overheating and allows for future maintenance. And 4. The quality of the connections inside the junction boxes is the final defense against electrical failure and fire. Now I want to hear from you. In the comments below, what's the most challenging wiring situation you've ever encountered? Was it retrofitting old knob and tube wiring, dealing with corroded aluminum connections, or pulling wire through a complex conduit run? Your field stories are a learning tool for everyone. If this guide to electrical wiring materials has empowered you to understand this critical system, please give this video a like and subscribe to Architect AI for more content that builds your expertise from the ground up.